Welcome to the Deep Dive. Today we're plunging into a world of immense power, quite a bit of unseen complexity, and some frankly brilliant engineering, high-pressure boilers. For this deep dive, we've pulled together the sources you shared with us, and our mission is really to unpack what these machines are, why they're so crucial for our world, and maybe uncover some genuinely surprising facts about how they work. Let's get right into it.
Absolutely. And I think what's crucial to understand, right off the bat, is that these aren't just some obscure machine sitting in a factory corner somewhere. They are quite literally the powerhouses behind so much of our electricity, our industrial output. Often unseen, maybe, but absolutely essential.
Okay, so diving into the material we looked at, what really defines a high-pressure boiler? What sets it apart? I mean, what kind of extreme conditions are we really talking about here?
Well, yeah, when we say high pressure,
Yeah,
it's far beyond what most people probably imagine. We're talking pressures above 80 bar.
80 bar. Okay.
Yeah, often soaring up to, say, 160 bar or even more. Think of it like a jet aircraft, maybe, standing on something tiny like a postage stamp, that kind of force. And temperatures hitting 540 degrees Celsius or even higher, their main job, to produce superheated steam under these intense conditions, mostly for, large-scale power generation and heavy industrial processes.
That is just an astonishing amount of force and heat. But why? Why push things to such extremes? What's the thermodynamic advantage? Why operate like that?
Right, that's the key question, why these extremes? Well, it boils down to efficiency. Operating at such high pressures and temperatures allows for incredible efficiency, often exceeding 90%.
90%.
Yeah, it's remarkable. It really pushes the boundaries, maximizing the energy you can get from the water and steam, minimizing losses. And this kind of design, it also means really quick startup times, better heat transfer, all in a, surprisingly compact structure for the amount of steam it kicks out, which makes them perfect for these huge power plants where every bit of efficiency counts, and you need to respond fast to demand.
The efficiency gains are really staggering. But okay, how did engineers actually manage this to push past those limits? This brings us to some pretty ingenious designs, right? My notes mention something called a Benson boiler. How does that one work, especially operating without a normal boiler drum? That seems counterintuitive.
That's a great point. The Benson boiler's genius is its once-through design. Basically, water is forced through one long, continuous tube. It gets heated gradually, goes past its boiling point, all in that tube. Critically, you eliminate that big, bulky boiler drum, the part that usually separates steam and water.
Oh, okay.
So it simplifies construction, saves on materials, allows for much faster startups, and really rapid changes in load. Very flexible. But, connecting this to the bigger picture, it gets even more mind-bending when you look at supercritical boilers.
Supercritical boilers. Okay, now that sounds like something from science fiction. What's happening there?
It kind of is. With supercritical boilers, the water is operating above its critical point.
Above the critical point,
Right.
meaning?
Meaning the pressure and temperature are so extreme, water doesn't really have separate liquid and gas phases anymore. It becomes this single sort of homogeneous fluid.
Wow, no boiling.
Exactly. There's no boiling in the traditional sense. And the huge advantage there is you skip the whole latent heat of vaporization thing, which boosts thermal efficiency even further. Plus, it allows for incredibly fast heat transfer and load changes, ideal for the modern grid. And then there's also the low-floor boiler, which is quite clever too. It uses superheated steam to actually evaporate the incoming feed water.
Steam to evaporate water. How does that help?
Well, the main benefit is it helps avoid scaling issues inside the boiler tubes, those damaging mineral deposits, that build up like plaque.
Ah, right. That clog things up.
Precisely. They reduce efficiency and can even cause failures. The low-floor design gets around some of that.
It really is incredible, the level of ingenuity here. So, okay, from these complex designs, let's shift to where they actually impact us. Where do these powerful machines power our world day to day? And I guess with such advanced systems, what are the big challenges? What makes them difficult to run?
You find them pretty much anywhere large-scale energy is needed. Thermal power plants, obviously, generating a huge chunk of our electricity, but also vital in refineries, petrochemical plants, various big industrial processes to think textiles, food production, anywhere needing massive amounts of reliable, high-quality steam.
Oh, okay. So they're really fundamental.
Absolutely. Now, as for challenges, yeah, there are significant ones. First off, the initial cost is incredibly high. These are major investments. Then you absolutely need highly skilled people to operate and maintain them. It's precision work. Mistakes can be, catastrophic. And a huge factor is water quality. They are very vulnerable to scaling and corrosion if the water isn't impeccably pure. That's a constant battle.
So high cost, high skill needed, and very sensitive.
Exactly. But despite all those complexities, their role in providing that large-scale power is, for now at least, pretty much irreplaceable.
So we've kind of journeyed through this unseen but utterly vital world of high-pressure boilers, from their frankly astonishing operating conditions and innovative designs to where they're actually used across industries and the inherent challenges that come with managing all that power.
And I think that's really the core takeaway for you listening. Next time you flip a light switch, or maybe use almost any product that needed some kind of manufacturing, just take a second to consider the immense high-pressure, high-temperature engineering that's working away tirelessly behind the scenes to make that possible. These boilers, they're truly complex marvels underpinning so much of our modern life, yet, as we said, mostly out of sight.